Matrix C is just given by the decomposition multiplicities of the cell modules. And we had a nice structure on these, some triangular structure in the sense that lambda has to be bigger than mu in order for this to be non-zero. So that means that we have an upper or lower, depending on your ordering, triangular matrix, which means that C will be invertible, and this actually makes sense. No, the proof is actually not very difficult. So similar statements are of course true in the original Deligne category, but somehow I never found a direct proof there. There was some proof of things like this going via classical invariant theory in quite complicated constructions. Of course, here that doesn't make sense. There is no classical invariant theory that you can rely on. So, but actually this is something which can be proved rather directly. So I'll try to sketch a proof. So let's for a second forget the decomposition of the functor into generalized eigenspaces. So we just take the original functor t acting on R of nu. So this is given by the object R plus 1 E times I for R given by the size of mu, and E such that this projective module is precisely isomorphic to that one. Okay, so the question is then which indecomposables appear here, or with which multiplicities the indecomposables appear. And then if you look at this basically means, so this was a primitive idempotent in AR, this is some idempotent in AR plus 1. It doesn't need to be primitive. It has a decomposition into primitive idempotents, and those primitive idempotents are precisely corresponding to the partitions which appear here. So the question what appears here is really which primitive idempotents do we have in this idempotent, which is the same as which indecomposable projective modules do we have in this module. And this can be rewritten as the induction from AR to AR plus 1 of this projective module corresponding to that primitive idempotent. It's just rewriting the same module. So then we can just apply some common tricks. So now we're actually, so we forgot about the J, so what we're calculating is just the summation over J of all these constants. So that's given or determined by how many times a certain projective appears in there. So in order to calculate how many times it appears, you have to calculate the dimension of the space of morphisms from this projective module to the corresponding simple. You all right? So we have some projective object here. We want to calculate the number of times that PR plus 1 kappa appears. So we just calculate the dimension of morphisms to the simple. And then we apply a junction. So we're actually calculating the number of times, the dimension of the space of morphisms from this projective to that module, or then again, just the number of times the corresponding simple appears in there. So of course now we've forgotten about the J. I'll just tell you how to get the J back in. Well, here we've got a restriction from AR plus 1 to AR. And so the J came from the decomposition of T with respect to some juicy Murphy element XR plus 1. So that XR plus 1 commutes with this subalgebra. So it decomposes this AR module into direct summands corresponding to some eigenvalue. And it turns out that when you plug in the correct definition, this J really means that we take not here the entire module, but the direct summand corresponding to eigenvalue J of XR plus 1. So that takes a little bit of fiddling around, but this is just the end conclusion that if we want to have AJ, we just take a direct summand corresponding to an eigenvalue. Okay, so this is some calculation of AJ. And so why does it imply this claim here? Well, we can reinterpret these constants Bj that I had here. So this is something we've already seen before, because when we restrict cell modules from AR plus 1 to AR, not simple modules, then we had a very nice description of which cell modules appear. Namely, they were given by always adding an arbitrary box or removing an arbitrary box. These were all the ones that we got. And then if we would restrict to the corresponding eigenspace of the juicy Murphy element, it was given by either the content if we add it, or content minus 1 or plus 1, depending on which point of view you take, if we remove it. So that means that this is the same as the restriction from a cell module, and then taking the jth eigenvalue again of the same juicy Murphy element, and calculating the number of times the corresponding cell module appears in there. So AJ might be a very complicated thing to calculate, but BJ in this expression is quite easy. And of course, both of them are related by some by the decomposition multiplicities of the cell modules themselves. So then, once we have this observation about A and B, it's not difficult to see that they are linked by twisting with C. So that's how we come to that theorem. So one nice thing here is that it really shows that this this functor t, which was given by tensoring with the generator. So on the paraplectic Lie superalgebra module category side, that's just tensoring with the natural module, which is the translation functor used there, is really related to the restriction functor in a very rigorous way. So that's what I meant the other day by saying that we can really regard this as translating Verma modules and translating simple modules. It's really connected up rigorously. That's just a side remark, of course. Okay, so this expression means that in principle we understand the coefficients corresponding to that functor. In principle, of course, because it involves the decomposition multiplicities as well as inverting some infinite matrix. In practice, it's not extremely useful yet. So the way to proceed is then to look at, funnily enough, representations of some temporally leap algebra. So that's what I'll get to now. So representations of some temporally leap algebra, and I have to say here that everything in this section was really heavily inspired by the same preprint that I mentioned yesterday with the 10 authors, who have some similar constructions for the paraplectic Lie superalgebra itself. So we don't really need their results, but the inspiration to do this whole construction came purely from looking at their work. Otherwise, I don't think we would have ever had the idea of making the construction that I will describe now. So this algebra, Tn infinity 0, is just some infinite version of the usual temporally leap algebra for parameter 0 or parameter square root of -1, depending on your usual convention. So it is, we see it as an algebra over Z. With generators ui for any integer I. And the relations are given by if we square any generator, we get 0. So usually you get some constant times this ui, but we get 0, which is the parameter here. And then the generators commute if they're not neighboring. And if they are neighboring, we get braid relations. Well, some type of braid relations. So the reason this algebra comes into play here is that it's a rather easy calculation to check that we get a representation of this algebra on the space of partitions as follows. So I call it sigma prime because the real representation, which is of interest, has yet to come. So if we say that the generator uj maps some partition lambda to this sum, so we use this matrix B, which has a very nice form, just adding a j box or removing a j minus 1 box. So that's basically what this is. We take some partition and we take all partitions that can be obtained by adding or removing a certain type of box. So in particular, if we have a given partition, there's at most one partition that can be obtained by adding some j box for a fixed j. If you have some partition and I want to add some 0 box, I can add it here, but clearly the next 0 box would be here, and there's never any possibility to add twice the same content. So this is quite easy to manage what happens here. So it's not very difficult to compute that is actually a representation of the temporally Lieb algebra. For instance, it's easy to check already. The diagram I've just drawn kind of shows it, that if you want to add twice the same content, you can't do that either. So that's why this thing squares to 0, for instance. That one is rather easily checked, etc. But the one that we're interested in is, of course, not that representation, but the same thing where I replace the coefficients b by the coefficients a. And because I know that this gives representation, I immediately know that this gives representation as well, because this is just given by twisting the space by some automorphism. So even though I don't know these coefficients really well, we know that this gives representation of the temporary Lieb algebra. And that is really the crucial step here. So what we could do then was, rather than really trying by brute force to compute these coefficients based on this expression, based on our in principle knowledge of C and B, is that we computed only some special cases which were still difficult but manageable, and then were able to derive the rest using the temporally Lieb relations and not the original theorem that we had there. So that was the strategy. So we have the following relations. The first one is easy to check. It just says what the generators of that representation do on the empty partition. And the second is rather more difficult to check, but still manageable. So the second property is that if lambda happens to be so that we can add some box with content j, then the action of u of j on that partition is really just given by adding that box. So this leaves open what happens in all the other cases, but so not only could we prove that sigma satisfies these two relations, it's also possible to prove that if some representation on the partition satisfies these two relations, then it is completely determined. So then we could really give some explicit description of what happens on different partitions. In other words, give the coefficients a, j. So it's not a very nice expression. It is a rather technical thing, but it is quite explicit. It says if you don't have an addable J box, you look in that column, you count the number of boxes there, you have to subtract that, the maximal thing there. So it is still quite intricate, but it is something explicit. It's not algorithmic, for instance. But I won't give the full statement. So I have to say that for the ordinary, the linear categories, so the one which would correspond to OSP, I don't think that the description can be made, or at least it's not known to be this explicit for the corresponding coefficients. So here somehow the end result is more concrete than in the classical case. Because a priori we didn't really expect to be able to compute these explicitly. Usually you wouldn't need them explicitly to have the description of the thick tensor ideals. It's something like determining the blocks. You don't need all the decomposition multiplicities in general to determine the blocks. This is a bit similar. You don't need all these coefficients explicitly usually to determine the thick ideals. The thick ideals are some kind of a rough description of these coefficients. But here we were able to have them even explicitly. So in particular, once we have them, it's just a matter of reading off what the thick ID is all. So I define the following full additive subcategory. So full additive thick. Corresponding to the following indecomposable objects. I take all of the R lambda which contain these two core. So I used that notation yesterday for like the kth two core. That we had there. So I take all partitions basically which contain that two core. So this is a different statement that's saying that is the two core of that partition. Just that two core needs to be in there. For instance, if I take k to be 0, this is just all partitions. If k is 1, then this is all the partitions except the empty partition, etc. So in particular, the entire category is equal to I0, which strictly contains I1, I2, etc. I just get one chain of subcategories. And then the theorem is that this set of subcategories is a complete list of thick ideals. So of course, perhaps you're wondering, why am I talking so much about thick ideals? Well, it's an immediate property, for instance, that this tensor functor that we have from the paraplectic linear category to the category of finite dimensional modules over some paraplectically superalgebra. This is an additive functor, and it is also a tensor functor. So that means that if we take the set of all objects which are cancelled by this functor, we get a thick tensor ideal. If some object is cancelled and then I tensor it with something else, I get something which will again be cancelled. So because it's a tensor functor, the kernel will be an ideal. Because it's additive, it will be an additive subcategory. And also, it is clear that it has to be thick. If direct sum of two objects is cancelled, then both must be cancelled individually. So the kernel is a thick tensor ideal. So here also I use kernel in some naive sense. In principle, usually when you talk about the kernel, you mean a set of morphisms. So this is a bit rougher. It just refers to the full subcategory of objects which are cancelled. No. But if you keep that response in mind, you will very quickly be correct. The second observation is that if we take some subcategory, namely the subcategory of objects in the paraplectic linear category, such that they are mapped to a projective module, so we define J to be the subcategory of objects which is mapped to something which is projective in some particular n, then that also gives me a thick tensor ideal. Again, for the same reason. If I take the tensor product of a projective module with a finite dimensional one, it is always projective still by adjunction, etc. So for the same reasons, also this is a thick tensor ideal. And I guess that Julian can guess which one it is. So this one will be iron. So these are two interesting things that we want to know what the kernel of this one is, because we understand the decomposable objects here. If you want to classify them here, you just need to know the kernel, and if you want to know which ones are projective, it's again a thick ideal. So it would be hard to determine these kernels or this pre-image somehow directly. But once we've classified thick ideals, and it is actually a rather elegant description, it's just one chain of them, it's not very difficult anymore to pick out the right one. So this idea goes back to Johnny Combs and Torsten Heidersdorf, who did this for the OSP case. So they classified thick ideals in the ordinary linear category and used that to answer those questions for OSP. But so the concrete answer here is given as follows. So the kernel of Fn is I n plus 1. And Fn of x is projective if and only if x is in In. So recall that In is bigger than In plus 1. So in particular, we find that we can interpret Fn if we restrict it to this subcategory and then quotient out everything in here. Because everything in here is in the kernel overall, and then if we restrict to that category, we get a functor to the category of projective modules over PEN. And because the tensor functor from the paraplectic Brouwer category was full, the functor coming from the Deligne category is still full. So this functor is full and essentially bijective. So I should maybe write F tilde. So we get a bijection between objects up to isomorphism, of course, and it is also full. So it is somehow a very close description of this. It's just a matter of finding which morphisms are killed before you get a diagrammatic description of the category of projective modules. So I think this is a very nice feature of the Deligne category. So we started from the paraplectic Brouwer category, which gave some module for describing invariance in powers of the natural module, something quite specific. And now we see that if we take the idempotent completion, the Karoubi envelope, we get a category which has some natural filtration. And in each quotient that we take, we find the category of projective modules for some paraplectic Lie superalgebra. And all the paraplectic Lie superalgebras are reached. So somehow all the information about all these categories is in some way contained in that paraplectic Deligne category, which I think is a very intriguing observation. Yeah, the whole, the same statement. You also get one chain, and it's also